A Van de Graaff generator is an electrostatic generator which uses a moving belt to accumulate electric charge on a hollow metal globe on the top of an insulated column, creating very high electric potentials. It produces very high voltage DC electricity at low current levels. It was invented by American physicist Robert J. Van de Graaff in 1929. The potential difference achieved by modern Van de Graaff generators can be as much as 5 megavolts. A tabletop version can produce on the order of 100,000 volts, and can store enough energy to produce a visible spark. Small Van de Graaff machines are produced for entertainment, and for physics education to teach electrostatics. Larger ones are displayed in some science museums. The Van de Graaff generator was developed as a particle accelerator for physics research. Its high potential is used to accelerate subatomic particles to great speeds in an evacuated tube. It was the most powerful type of accelerator of the 1930s, until the cyclotron was developed. Van de Graaff generators are still used as accelerators to generate energetic particle and X-ray beams for nuclear research and nuclear medicine. Particle beam Van de Graaff accelerators are often used in a tandem configuration. First, negatively charged ions are injected at one end towards the high potential terminal, where they are accelerated by attractive force towards the terminal. When the particles reach the terminal, they are stripped of some electrons to make them positively charged, and are subsequently accelerated by repulsive forces away from the terminal. This configuration results in 2 accelerations for the cost of one Van de Graaff generator, and has the added advantage of leaving the complicated ion source instrumentation accessible near ground potential. The voltage produced by an open-air Van de Graaff machine is limited by arcing and corona discharge to about 5 megavolts. Most modern industrial machines are enclosed in a pressurized tank of insulating gas. These can achieve potentials of as much as about 25 megavolts. A simple Van de Graaff generator consists of a belt of rubber, or a similar flexible dielectric material, moving over 2 rollers of differing material, one of which is surrounded by a hollow metal sphere. 2 electrodes, 2 in the form of comb-shaped rows of sharp metal points, are positioned near the bottom of the lower roller, and inside the sphere, over the upper roller. Upper comb is connected to the sphere, and lower comb to ground. The method of charging is based on the triboelectric effect, such that simple contact of dissimilar materials causes the transfer of some electrons from one material to the other. For example, see the diagram. The rubber of the belt will become negatively charged while the acrylic glass of the upper roller will become positively charged. The belt carries away negative charge on its inner surface while the upper roller accumulates positive charge. Next, the strong electric field surrounding the positive upper roller induces a very high electric field near the points of the nearby upper comb. At the points, the field becomes strong enough to ionize air molecules, and the electrons are attracted to the outside of the belt while positive ions go to the comb. At the upper comb they are neutralized by electrons that were on the comb, thus leaving the comb and the attached outer shell with fewer net electrons. By the principle illustrated in the Faraday ice pail experiment, that is by Gauss's law, the excess positive charge is accumulated on the outer surface of the outer shell, leaving no field inside the shell. Electrostatic induction by this method continues, building up very large amounts of charge on the shell. In the example, the lower roller is metal, which picks negative charge off the inner surface of the belt. The lower comb develops a high electric field at its points that also becomes large enough to ionize air molecules. In this case, the electrons are attracted to the comb, and positive air ions neutralize negative charge on the outer surface of the belt, or become attached to the belt. The exact balance of charges on the upgoing versus downgoing sides of the belt will depend on the combination of the materials used. In the example, the upward moving belt must be more positive than the downward moving belt. As the belt continues to move, a constant charging current travels via the belt, and the sphere continues to accumulate positive charge until the rate that charge is being lost, through leakage and corona discharges, equals the charging current. The larger the sphere and the farther it is from ground, the higher will be its peak potential. In the example, the wand with metal sphere 8 is connected to ground, as is the lower comb. Electrons are drawn up from ground due to the attraction by the positive sphere, and when the electric field is great enough the air breaks in the form of an electrical discharge spark. Since the material of the belt and rollers can be selected, the accumulated charge on the hollow metal sphere can either be made positive or negative. The friction type of generator described above is easier to build for science fair or homemade projects, since it does not require a high voltage source. Greater potentials can be obtained with alternative designs for which high voltage sources are used at the upper and or lower positions of the belt to transfer charge more efficiently onto and off the belt. A Van de Graaff generator terminal does not need to be sphere-shaped to work, and in fact, the optimum shape is a sphere with an inward curve around the hole where the belt enters. A rounded terminal minimizes the electric field around it, allowing greater potentials to be achieved without ionization of the air or other dielectric gas surrounding. Outside the sphere, the electric field becomes very strong, and applying charges directly from the outside would soon be prevented by the field. Since electrically charged conductors do not have any electric field inside, charges can be added continuously from the inside without increasing them to the full potential of the outer shell. Since a Van de Graaff generator can supply the same small current at almost any level of electrical potential, it is an example of a nearly ideal current source. The maximal achievable potential is roughly equal to the sphere radius r multiplied by the electric field Emax, at which corona discharges begin to form within the surrounding gas. For air at standard temperature and pressure, the breakdown field is about 30 kV per centimeter. Therefore, a polished spherical electrode 30 cm in diameter could be expected to develop a maximal voltage Vmax equals R Emax of about 450 kV. This explains why Van de Graaff generators are often made with the largest possible diameter. Thank you for watching. Do like, share and subscribe.